Welcome to the Problems Channel Season 2, Episode 12, the episode which I titled Integration of Binomial Differentials, because in this episode we will do just that. We will discover a way to integrate binomial differentials. But before we deep dive into the underlying mathematics, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from working with the material that we present on this channel is for you to go to the homepage of this channel, and at the top of that page in the channel's trailer section, find the episode titled The Problems Channel How To. We recommend that you watch that episode in its entirety and follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. And if you have any questions, then by all means do ask. Find an episode that is of interest to you, use the comment section under that episode, and I will do my best to answer all of your questions. In the mathematical problem S3E12, we were asked to find a way to integrate the so-called binomial differentials, which, as we shall discover in a moment, pretty much when it comes to the theory of integration, have the following interesting shape that is of interest to us in this context. A constant real number a plus a constant real number b multiplied by the integration variable z, when the entire linear combination is raised to the power p, and that formation is multiplied by the integration variable z raised to the power q, and the integration in this case is carried out with respect to the variable z, where p and q are generally rational numbers, and the symbols a and b stand for a certain constant real number. In general, a way in which you are expected to solve the mathematical problem S3E12 amounts to the analysis of when the given differential can be integrated in the so-called closed form, or it can be represented as a finite combination of elementary functions. And here, the story of binomial differentials pedantically begins with the differential that has the following structure shown on the left side of your screen. Here we begin with the integration variable x that is raised to the power m multiplied by the following expression: constant real number a plus a constant real number b multiplied by the integration variable x raised to the power of n, and that formation a plus b times x to the power of n itself is raised to the power of p, where in general again we begin with the case when the numbers m, n, and p are rational. This is the scope of our universe, so to speak, when it comes to the integration of binomial differentials. And first we begin with the case where the number p is only nominally rational, but in general this is a whole number. What can we say about the integrability of this so-called binomial differential? In that case, in the so-called closed form, or as a representation via a finite combination of elementary functions. Well, let's say our exponent m can be represented as, because it is a rational number, we will take it that is representable as a whole number c divided by whole number d, and likewise the exponent n is representable as a whole number k divided by another whole number L. What should we do in this case? Well, it is evident that in this case, we want to compute the least common multiple of the denominator of the rational number m, d, and the denominator in the rational number n, l, d, l. Again, LCM stands for least common multiple, or the smallest integer, which is divisible at the same time by both the integer d and the integer l. Why is that? Well, in this case, it should be evident that the following substitution, t raised to the power of lambda equals x, takes care of business because it will unfold this binomial differential into a function that is rational in the new variable t. How can we see that? Well, from this substitution, what do we have? From this substitution, we have the following trivial result. Dx will be equal to lambda times t raised to the power lambda minus 1 dt. That much is evident. This is nothing very complicated. Now let's rearrange our differential in terms of the new integration variable t. What will we have? We then will have x raised to the power m plus b, x raised to the power of n raised to the power of t dx will be equal to what? It will be t raised to the power lambda times m times a plus b t raised to the power lambda times n. Then the whole thing is raised to the power of p, and then we need to substitute the first differential, lambda t lambda minus 1 dt. And now let us carefully analyze what just transpired. The number lambda times m will be what? Because lambda was chosen to be the least common multiple of the denominators d and l, it is evident that the number lambda will be divisible by d. So this number over here, lambda times m, will be an integer. What about the number lambda times n? Again, because lambda was chosen to be the least common multiple of the numbers d and l, the product lambda times n, where l is in the denominator, will be an integer. So here we will have another integer. That much is evident. So what do we have for our new variable t? Integer, integer, integer by assumption. And this is what? This is integer. In other words, what we have here, this expression over here, will be a function that is rational in t. And at this point, the theory of integration of rational functions takes over. This is the previously studied material. In this particular context, it is not of interest to us, and we want to consider the next case when the exponent p is not an integer but is a number that is rational. In the next case that we want to analyze, the number p is not an integer but is a number that is rational. That means that in this case, p will be representable as the ratio of two whole numbers, r and s, and we will agree that s is not equal to plus minus 1. So, for example, these numbers work out in such a way that the number p is rational right away. What is the winning tactical maneuver in this case? Well, in this case, we want to get rid of this pesky character over here and introduce the following substitution. X raised to the power of n is equal to z. You see, this is the substitution. From here, what do we have? We have x is equal to z raised to the power 1 over n. From here, it follows that for the first differential, we will have 1 over n times z raised to the power 1 over n minus 1 dz. And once we substitute these results back into our expression, what will we have? X raised to the power of n times a plus b times x to the nth power raised to the power p dx. This is our original binomial differential, unfolds into what? 1 over n, 1 over n. Then we will have a plus b times z. You see, this is our differential is emerging, raised to the power of x times z. Now let us carefully calculate what is going on over here. X raised to the power of m will be z raised to the power of m over n. We have that much, and then we need to multiply all this by this, by the remainder of the first differential of dx. Here we will have 1 over n. So 1 over n plus m over n minus 1 dz. So we will have m over n plus 1 minus 1, and then the first differential dz. You see what is going on? That was a very straightforward manipulation. Now, because this number is somewhat clunky to work with, let us agree on the following idea. So we will designate m plus 1 over n minus 1 as the number q. You see, this is our designation. M plus 1 over n minus 1 is q. And where did this come from? Well, this came from the happy marriage between x raised to the power of m and the first differential dx in terms of dz. You see, x raised to the power of m is the same as z raised to the power m over n plus 1 over n minus 1. And n is 1 in the same denominator. M plus 1 over n minus 1 is q. And this is our, essentially, under this agreement, what do we have here? Here we have precisely our number q. This is our agreement. This is what we have in our original problem statement. And again, this in a way comes back to our original case when p was an integer. So here we want to consider two cases: when q is a whole number, and when aq, the number q, is not a whole number but is a number that is rational. Wonderful. We now take the number which we arrived at in the previous segment, q, which we define over here, and assume as the first assumption that that number turned out to be whole. What does that mean? That means that our, in general, numbers that, remember, m and n leftovers from the official binomial differential, which these numbers are rational. It so happened that the number m plus 1 over n minus 1 is whole. And what does that mean? Well, 1 is a whole number. That means that m plus 1 over n plays out to be a number that is whole. So in this case, which substitution will slay this particular integral and make it integrable as or represented as a finite combination of elementary functions? Evidently, the following substitution: a plus b times z raised to the power of 1 over s is equal to t. Because remember, now we have it in our second case when the number p is genuinely rational, it's not an integer. That means that number is representable as the ratio of two integers, r and s. S is definitely not plus minus 1 because otherwise p stops being a genuine rational number, and we do not want to play all these clever games with equivalence classes because for example, number 3 belongs to the same equivalence class as 3 over 1, for example. We do not want to deal with that. We do not want to mess with all this cleverness. We want a genuine rational number, and then this is what we have. And in this case, when we raise both sides of this new substitution, t is our new integration variable, to 1 and the same power s, what will we have? We will have a plus b times z equals t raised to the power of s. But s, remember now, is what? Is a number that is whole. So now we're beginning to manufacture a function that is rational in t. Now we move a to the other side. We move a to the other side of the equal sign. We have t raised to the power of s minus a. And then what do we have for the first differential? Well, we have, let's write it down this way, b times the first differential dz will be equal to, let's save some space, s times t raised to the power s minus 1 times dt, and we remember that z in this case came out to be what? T raised to the power of s minus a over b, and then our expression here, a plus b times z raised to the power of r over s, because remember, r over s is our genuine rational number p, times z raised to the power of q, where q is a whole number by assumption, by the temporary assumption, dz, unfolds into what? This horrible looking mess becomes t raised to the power of r. Evidently, remember one more time, I'll write it down over here, a plus b z, if you need to catch this, to the power 1 over s is equal to t. This is our initial substitution. So when we raise both sides of this equality to the same power r, this becomes p, and this becomes t raised to the power of r, t to the power of r. Now we just have to carefully unwind our z raised to the power of q. It's this expression, b raised to the power of q times t raised to the power of s minus a raised to the power of q. So far so good. Z raised to the power of q, everything here raised to the same power q, times the first differential. So what do we have? Times s over b times, what else? T raised to the power s minus 1 times dt. Now let us again carefully analyze what just transpired. R is a whole number. R is a whole number. Here we don't care. T raised to the power of s, another whole number. Q is a whole number by assumption. And then t, whole number minus a whole number is a whole number. The set of whole numbers is closed under subtraction. The difference between any two whole numbers is a whole number. So what do we have? We have our new integration variable t everywhere raised to a power that is a whole number. Thus, we again manufacture a function that is rational. At this point, the theory of integration of rational functions takes over. We're not interested in this particular case in the context of this problem. And next, we want to consider the case when the number q, which is shown over here, is not a whole number, not an integer, but is a number that is rational. Finally, we consider the case when the number q is not an integer, but it's a number that is rational. And what do we do in this case? Well, in this case, we work with the factor z raised to the power of q, and we represent it which way? Let's do it here. Z raised to the power of q is equal to z raised to the power of q times 1. We begin with this maneuver, and that will be z raised to the power of q times z raised to the power of p divided by z raised to the power of p. You see, we will try to sneak this variable under over here with the same power. So what does that mean? That means that that will be z raised to the power of q plus p divided by z raised to the same power p. And then in this case, what will happen? Well, our differential will be written as follows: a plus b times z raised to the power of p times z raised to the power of q dz will be, again, let's write it here this way: a plus b times z divided by z raised to the power of p. You see, this z raised to the power of p crawls under into the denominator of this linear combination times z raised to the power of p plus q times dz. And again, from the theory of integration of rational functions, we already see where this is going. If this number, which again, remember, p is rational, genuinely rational. Now q is rational, so if the sum of two rational numbers comes out to be an integer, so if p plus q comes out to be a number that is genuinely whole number, is a number that is whole, it comes out to be a whole number, this is a whole number, then what will happen? Well, then remember again, p is representable as r over s, is the ratio of two whole numbers. And then in this case, we will do precisely that. We will say that a plus b raised to the power of z divided by z raised to the power of 1 over s will be t. You see, this is the substitution. Will take care of business. From here it follows what? That a plus b times z over z is equal to t raised to the power of s. S now is an integer, a whole number, and from here it follows what? It follows that a plus b times z is equal to z times t raised to the power of s. This is middle school arithmetic. Now we move this summand, let's say, over here. So we have what? A is equal to z times t raised to the power of s minus b. You see? And from here it follows what? From here it follows that z is equal to a times t raised to the power of s minus b to the minus first power. Take the first differential of z, dz. This will be, again, a rational function in t. We don't have to torture this. And this will take care of the differential dz. Okay, let's write it down just to be thorough. dz will be what? Will be minus times, it will be a s t raised to the power of s minus 1 divided by t raised to the power of s minus b squared dt This is our first differential. So here we have a function that is again rational in t. S is a whole number, S is a whole number, S minus 1 is a whole number, this is a whole number, so we have a function that is rational in t. So this takes care of the first differential over here. This number over here, let's take a look. It will be this expression raised to which power? Integral power, exactly, because now we assume that p plus q is an integer whole number. And then here this expression will raise to the power r and r. This will be t raised to the power of r. Again, is what? It will be a product of rational functions. That the whole thing will be rational again. And precisely these are the cases when the theory of integration of rational functions takes over, and we thus arrive at the following. Remember, three cases. The case number one, we had what? P was an integer. The second case, Q was an integer. And now we had P plus Q. All three numbers are integers. And apparently, all this information was known back then in the let's say, second half of the 17th century to Isaac Newton. Apparently, from the works of Isaac Newton, we know that he was aware of this information, but only in the middle, in the 1850s or thereabouts, in the middle of 19th century, the Russian mathematician Chebyshev, he showed that these are the only cases when the binomial differential that we saw, this one, or its equivalent, x raised to the power m a plus b x raised to the power of n dx, remember this, and this was 1 over n, and then this whole thing. So these two integrals, these two differentials right here, are integrable only in three cases: when the number either p or q or p plus q is an integer, then this whole mess over here, or this, is representable as a finite combination of elementary function. And that was proved, actually, formally. It was proved by Chebyshev in 1850s or thereabouts, again in the middle of 19th century, that these are the only cases where the integrals shown over here have antiderivatives that are representable as a finite combination of elementary functions, or integrable in the so-called closed form, which means for us now, and again, if we go back to our nomenclature that we use over here for the official binomial differential, then what does it mean? So we have the numbers p, the number p here, or the number m plus 1 over n is an integer, or the number p plus m plus 1 over n is an integer. So we have p is an integer, m plus 1 over n is an integer, or m plus 1 over n plus p. If any one of these three numbers, in terms of our official binomial differential, is an integer, is a whole number, then definitely the integrals over here are representable in closed form or as a finite combination of elementary functions. As such, we want to now investigate the case when the numbers p and q, in this case p and q, in the differential shown over here, which is basically our original differential multiplied by n, if we carry it over here, but the multiplicative constant does not really affect the technology in any meaningful way, so we will concentrate on this expression over here when the numbers p and q are rational. Very good. So now is an opportunity for you to rise and shine. This is also what you were expected to produce while you were solving this problem, because now we want to step away a little bit from the cases when things are integrable right away. We know the three cases when either the number p is an integer or the number m plus 1 over n is an integer, or q is an integer, or p plus q, or p plus m plus 1 over n is an integer. In any one of these three cases, definitely the integral at hand is representable as a finite combination of elementary functions. Now we want to creatively somehow manipulate our integrals in such a way that we can see for ourselves how things will work when the numbers p and q are rational. One idea here, again, this was the opportunity for you to rise and shine and show your technical creativity and ingenuity. Think like a mathematician and find an approach to unwind this situation into a favorable scenario and precisely find a way to integrate the binomial differential shown over here. One such way is to synthesize or work out, come up with somehow what's known as a recurrence relation, where, for example, the numbers p and q, if they are positive, then we want to decrement them by some arbitrary whole number. Let's say 1 is a popular number, and then whittle them down, the numbers p and q, into the neighborhood of 0, plus 1, minus 1, somewhere in that area, so we can reduce the material that we have to fight with to hopefully some terminal case which we can deal with. Conversely, if the numbers p and q are negative, we want to bump them up and bring them up to the vicinity of 0, plus, minus 1 again, to a terminal case which hopefully we can deal with. So how can we do that? Well, here is one way. We start with middle school algebra. We go like this. In our given expression, in our integrand, we bump only the power p by 1, for example. You can you can experiment with other possible maneuvers too, but here is one maneuver that will work. So we take a plus b times z raised to the power p plus 1 times z to the power of q. And this is basically it. We unwind this guy. What do we write? A plus b z raised to the power of p times a plus bz times z to the power of q. And then what will we have? Well, we multiply these two summands over these two factors. What will we have? We will have a times a plus bz raised to the power of p times z raised to the power of q, plus, what else? Plus, we will have b plus b raised to the power a plus bz to the power of p, b, z, b times a plus bz raised to the power of p. Here we have one copy of z, another q copies of z, so times z raised to the power of q plus 1. See, this maneuver should be understood by everyone. It's nothing complicated, but again, the whole idea here is that the symbolic shuffling that follows is secondary. It's the idea that is generated by you as a mathematically inclined thinker is what counts. Coming up with this idea is doing mathematics. Everything that follows is either not doing mathematics or doing lesser mathematics, depending on how strong your stance on this issue is. So now we omit the intermediate manipulations, and we write a plus b times z raised to the power of p plus 1 times z raised to the power of q is equal to a times a plus b z raised to the power of p times z raised to the power of q plus b a plus b times z raised to the power of q times z raised to the power of q plus 1. You see, this is an evident, a baby in some sense, middle school algebraic identity, if you will. There's nothing complicated going on over here. What do we do next? Well, this is a finite sum we integrate without worrying about uniform convergence and all these horrible things. And what do we have? Well, what do we have on the left-hand side of the equality that we established? Well, p is raised to the power p plus 1. So in our definition, we have integral j p plus 1 q is equal to what? A times integral j pq plus what? B times, here is q is raised to the power of z raised to the power of q plus 1, jp q plus 1. Voila, we have our first equation, first relation. And now what is the next idea? Well, the next idea is to do the following. Here, for the second equation, we want to take our integrand again, but this time we want to bump up both powers, p and q, by 1. So we write, what is this? A plus b z raised to the power of p plus 1 times z raised to the power of q plus 1. And now we differentiate over z this expression once d over dz of this expression. Well, this is a product of two functions. We know how to do that. This is not particularly difficult. B times p plus 1 times a plus b z raised to the power of p times z q plus 1. You see, the first derivative of this expression, p plus 1, comes down, times the derivative of bz is b, p plus 1, and this whole linear combination is raised to the power that is less than 1 than this one. P plus 1 minus 1 is p times the second function plus, what's the deal over here? Well, our first factor, a plus bz raised to the power of p plus 1 times what? Q plus 1 times z raised to the power of q. You see, this is, again, nothing extraordinary. This is, again, generating this idea, pumping these exponents up by 1, and then differentiating like this, and then taking the integrals, okay, of both sides. Now, this represents doing mathematics. This is thinking like a mathematician. Anything else that follows after that, it's not really mathematics, but something lesser than mathematics. So what do we do here? Well, the integral of the full differential over here, the derivative, integration and differentiation are the what? Are the converse operations, just like subtraction is the converse of addition, division is the converse of multiplication, and so on. So here we erase this and we obtain right away what? B times p plus 1 is a constant, and what do we have here? Let's carefully erase this integral and just rename it into what we have. It's q plus 1. This is our integral j p q plus 1. You see, j p q plus 1. Do we have this integral anywhere else? Yes, we have it right here. And what is this integral modulo this constant, multiplicative constant over here? Well, this is p plus 1. So if we erase all this carefully, we know where it came from. q plus 1 plus q plus 1 times j p plus 1 q. You see, this is it. So this is our second. This is our second relation. Now we have two equations, two relations, and from these relations, what can we do? Well, we can solve these two. We can do two things we're about to do. In the first thing, we want to directly express this integral jpq in terms of what? First, when p is not minus 1 in terms of this animal, and second, when q is not minus 1 in terms of this animal. That's the one thing that we will do. The next thing that we will do after that, we will step in the opposite direction. We will express our integrals jp plus 1 q and jpq plus 1 via this integral, and then in either one we will bump p down. So here we will have p minus 1, and the second time when we bump the q down, we will have q minus 1. Thus we will have four recurrence relations that we will be able to exploit, and we manufacture them as follows. As we explained in Season 1, Episode 2, it is a good idea for you to put this video on pause, walk away from the computer, and complete this task from here onward on your own. Do it correctly and by yourself, but as a guidance. On the top, I kept the definition of our integral j of p and q, two variables. P and q is the same. P and q are rational numbers. A, b are two constants. And the two expressions that we developed in the previous segment, I lifted them up into equation number 1, which connects the integral j of p plus 1q with the integral j of p and q and the integral j of p and q plus 1. That was our first relation. Remember how we did it? We bumped the power of our number p in the integrand by 1, unfolded the product into very straightforward algebraic manipulations, integrated both sides, and voila, we arrived at this expression. And the equation number 2, it didn't fit in one line, it split over 2, but we have this expression here. This is the multiplication sign, this is the product, and these two terms over here. How did we obtain this equation? Again, this next time we bumped up these powers p and q by 1, differentiated the whole thing with respect to z once, used the rule for computing the derivative of a product of two functions, integrated the result through, boom, and that's how this expression came about. So now what we want to do first is assume that the number p is definitely not 1. Definitely not 1. Why? Because we will be dividing by p plus 1 in this case. And what does that mean? That means that we want to express our integral j of p and q, in terms of the integral j of p plus 1 q. And what does that mean? That means that in the second expression, we want to express this integral j of p q plus 1. See, important here, we pay attention, j p q plus 1 in terms of the rest of the material, and put it into the equation number 1. But here, look, in the equation number 1, we have a product b times j of p and q plus 1. What does it mean? It means that from the second expression, we need to only carve out this guy, b times the integral j of p q plus 1. P plus 1 will be the factor by which we will divide. And that's what we have essentially here. I showed in green, b times the integral j of p and q plus 1. This is this side, the left-hand side of the equality of this equal sign, divided by p plus 1, divided by p plus 1. This is transparent. And then we carry this guy to the left-hand side with the minus sign, minus this guy, q plus 1 times the integral j of p plus 1q times the integral j of p plus 1q divided by p plus 1. This is, again, straightforward middle school arithmetic. There is nothing complicated over here. What do we do next? Well, now that we have the image of b times the integral j of p and q plus 1, we inject it over here. I say this way. We take this and inject it over here in the equation number 1. So we write it down. The integral j of p plus 1q, this is equal to a times the integral j of p and q, this guy. And instead of this, we inject the right-hand side of this. So basically, we bring this result down. This is as straightforward gets. We have our two summands added, and what do? Well, we now solve this equation for the integral j of p and q. Game over. This is literally upper middle school curriculum. Nothing complicated going on. So we write down the expression over here. Remember, this integral has the factor of a in front of it, so we will be dividing everything by a. And what do we have? Well, the first term that we can write down right away is this. Carried over to the left-hand side of the equal sign, it will be what? With the minus sign. Don't forget the minus sign. So it's this summand carried over with the minus sign divided by a. So this is how a times p plus 1 makes it into the denominator. Again, straightforward arithmetic, nothing to do with highbrow mathematics. And once we bring this summand over to the left-hand side of the equal sign, we'll have one and the same integral j of what? P plus 1q. And what will we have on that side? We will have the expression that looks as follows: 1 plus q plus 1 over p plus 1. And what is this? Well, p plus 1 over p plus 1, p plus 1 plus q plus 1, p plus q plus 2 over p plus 1. This is, again, middle school arithmetic, and this is what we have. P plus q plus 2 in the numerator over a. Don't forget, we have to divide all this beautiful mess by a times p plus 1, and voila, this is our integral. This is, I showed it in red, jp plus 1q. And again, what does that mean? Well, it means that if the number p is negative, then we can iterate this recurrence relation by bringing p by an arbitrary whole number. This time it's number 1. We increment it by 1 until we bring it into the vicinity of 0, plus 1, minus 1, something in that neighborhoods. Hopefully the terminal case that will ensue will be manageable. And if that is not enough, now we will do the similar maneuver with the number q. So in the next segment, we will pretty much do the same maneuver almost, but this time we will be expressing the integral j p plus 1 of q in terms of this, and then we will be putting the image of this into over here and express this integral in terms of this integral shown over here. If in the previous segment we assumed that the number p was distinct from -1, now we assume that the number q is distinct from -1 because we will be dividing by the number q plus 1. And in order to make sure that this division is legal, we will make this assumption. And now the objective is to express the integral j of p plus 1q from the second equation in the given material, and inject this result into the equation number 1 so that we will have only two things left in the final expression: the integral j of pq sought after and the integral j of pq plus 1. Not p plus 1q, but pq plus 1. And again, this is straightforward arithmetic. This is not even mathematics. I present this manipulations here as a reference with the correct response. This is not the only way to do it. This is a way, but nonetheless, it leads to the correct result as such. From the equation number two, look at this. From the equation number two, under the assumption that the number q is distinct from -1, we express the integral j of p plus 1 q. Is this integral? This is trivial task. We take our summand shown on the left-hand side of the equal sign divided by q plus 1. So this comes down here divided by q plus 1, this result shown in green. And then we carry this summand over the equal sign with the negative sign. We keep b times p plus 1 and divided by q plus 1, q plus 1, q plus 1. This is our integral j of p q plus 1, p q plus 1, this integral. That's it, game over. We now take the right-hand side of this equal sign and drag it into the equation number 1. Here, we inject the right-hand side of this relation into the left-hand side of this relation, equation number 1. And this is what I wrote over here. This is what this summand comes here. The minus b and all this beautiful mess comes over here, minus b times p plus 1 over q plus 1 times the integral j of p q plus 1 is equal to what? Well, this is our friend, the integral a times j of p and q, this is the guy right here, plus b times the integral j of p and q plus 1. Well, it comes here as it is because this is precisely the material which we want to work into the recurrence for this integral. That's it, game over. We simply carry this summand over the equal sign and divide everything by a. This is it. So this is what I wrote over here. The value of the integral j of p and q is equal to this summand. Now, this time taken with the plus sign, we pay attention, plus sign. This divided by what? A times q plus 1. Q plus 1. It is legal because q is assumed to be distinct from -1. This. And now to this summand, from this summand again, we subtract this b times the same essentially integral. And what will we have once we factor minus b times this integral? Well, we will have 1 plus p plus 1 over q plus 1. We bring these ratios, these fractions under one denominator, so what will we have in the numerator? Q plus 1 plus p plus 1, which is q plus p plus 2, and in the denominator, q plus 1. So this is what I have over here, minus b times p plus q plus 2 over a times q plus 1. Game over, but this time we multiply this by what? The integral j of p q plus 1. I showed it in red specifically so that we have it front and center. And what does this recurrence relation allow us to do? This recurrence relation allows us to take, for example, initially negative q and iterate it by adding an arbitrary whole number, this time 1 to it, until we bring it up to the vicinity of 0, plus 1, minus 1, somewhere in there, depending on the favorability of the material that unfolds in these terminal cases. Sometimes maybe we will work with minus 1/3 or plus 2/3. It all depends on how things will work out. In the terminal case, we can play games over here, but now we have two recurrence relations. In the first recurrence relations that we deduced in the previous segment, we had the integral j p plus 1 of q. So this allows us to iterate p up closer to 0, plus 1, minus 1. And this relation allows us to iterate q, the number q, by 1 up again into the vicinity of 0, positive 1, negative 1, somewhere into the material that we hopefully can handle in the terminal case and integrate the given function in its closed form or as a combination, finite combination of elementary functions. Now in the next two segments, we will go in the opposite direction. Instead of having the recurrence relations in which p or q is incremented by 1, we will have the same numbers, p or q, decremented by 1. The next maneuver may come across as complicated, but it's not complicated at all. The idea here is just to carefully manipulate the variable p eventually by replacing it with p minus 1. So idea here as a first step is to express our integral j of p plus 1 q. You see, p plus 1 q, p plus 1 q, p plus 1 q, and p plus 1 q in terms of just the integral j of p and q. And then if in that case we will iterate p down by 1, replace p with p minus 1, so this will become the integral j of p and q exactly, but then in the end we will have the integral j where the variable q is what it is, but p is replaced by p minus 1. So how do we do that? Well, we go to the previous segment, and then we replace, express again the integral b times j of p and q plus 1 is this guy, see right here, because this is what we have in the formula number 1. Formula number 1, we have this, and we have almost precisely the same material here. So we grab this guy, move this summand to the left hand side of the equal sign, divide everything by p plus 1, p plus 1, p plus 1, and this is what we have over here. This summand goes here divided by p plus 1, and then this summand comes here and divided by p plus 1. So that's what we have. This is it. Game over. We now put the expression for the integral j of p plus 1 q in this formula here. This is here, and then this material comes down here again. Look at this. Now, however, remember, first time we wanted to express this integral in terms of this one. Here we do the opposite. We express this integral in terms of this one. So we carry this summand to the left-hand side of the equal sign. Here it will with the minus sign. Here it means that it will come here with the plus sign. And what we will have again? Well, we will have the same, we will have our favorite 1 plus q plus 1 over p plus 1. This will be our sum again. P plus q plus 2 over p plus 1. This is exactly what we have, and this is what I wrote over here. This will be on the left hand side. That means that the whatever was in the numerator here goes into the denominator of on the other side of the equal sign, and whatever was in the denominator on the left hand side becomes a numerator on the right hand side. But here, look at this. This summand overhead already had p plus 1 and p plus 1. They cancel each other out, and that's what we have. Our favorite free-floating term, so to speak, divided by p plus q plus 2. Where did this come from? From this summand right here, this sum right here. And what else do we have? Well, we have our integral integral j of p of q over here. And what is the factor in front of it? A. But now we basically take our fraction that we had on the left hand side, we flip it upside down. That's what it is, flipped upside down. P plus q plus 2 goes into the denominator, p plus 1 in the numerator. That's it, game over. Now we roll through this relation shown over here, and uniformly, meaning mechanically, every time we see p, we replace p with p minus 1 as shown over here in blue. P becomes p minus 1. P minus 1 plus 1 becomes p. Boom. Here it is, the integral j of p and q. Wonderful. Nothing to change over here. In this denominator, what do we have? P becomes p minus 1 plus 2. Minus 1 plus 2 is plus 1. P plus q plus 1. Boom. Which power is this linear combination raised to? Well, here, in the previous expression, it's p plus 1. But now p becomes p minus 1. P minus 1 plus 1 becomes p, as shown over here. Pay attention, p. Z, because it's shown over here with the exponent q, which does not depend on p, percolates down as it is, q plus 1 plus a. Now, p plus 1 becomes what? Becomes p, because p is replaced by p minus 1. You see? P minus 1 plus 1 becomes p. And in the denominator again, this p becomes p minus 1 Minus 1 collides with plus 2. Plus 1 comes out. P plus Q plus 1. That's it. But here in this integral, P becomes what? Remember our iteration down when we iterate this down by 1. Integral j of P minus 1 shown in red. P minus 1. And Q is the same. So this is our third recurrence relation that gives us weaponry in case when P, this time we assume that because we're dividing by P plus Q plus 1, P plus Q plus 1, we precisely assume that P plus Q is distinct from -1. P plus Q is not equals -1. And in this case, we use it when? We use it when P is positive. We try to iterate it down, again, bring it to the vicinity of 0, plus 1, minus 1, somewhere in that neighborhood, so that the terminal case is favorable to us. We can handle it, and the integral that comes out in the terminal case is precisely expressible as a finite combination of elementary functions, or the integral can be evaluated in the so-called closed form. Now, if this maneuver is understood, the fourth and the final recurrence relation will have the similar material over here, but instead of the integral j of P minus 1q, it will be what? Integral j of P q minus 1. And how do we do it? Well, we proceed as follows. For our final recurrence relation, we pretty much repeat the steps that we took in the previous segment again and express the integral j of P plus 1 q, j of P plus 1 q from the equation number 2. From the equation number 2, we express it like so. Again, that manipulation is transparent. We take the left-hand side divided by q plus 1, left-hand side, divided by q plus 1, and then we bring this summand over the left-hand side to the left-hand side of the equal sign with a negative sign. B times P plus 1 over Q plus 1 times the integral j of P Q plus 1 this time. And we basically put this right-hand side image of this expression. We grab it, bring it to the left-hand side of the equation number 1. Basically, this summand becomes this summand, and this summand becomes this one. And then we say equal to, again, a times the integral j of P and Q, j of P and Q plus this this expression right here, b times the integral j of P and Q plus 1. And that's it. Essentially, game over. Now, instead of expressing our integral j of P and Q in terms of the other integral, we go the other way. We express this integral j of P and Q plus 1 in terms of the integral PQ, and then we iterate things down. How do we do that? Well, we write down the expression for this integral by doing essentially what? By doing essentially keeping our free-floating term over here. It's shown over here. Then we bring this term to the right-hand side of the equal sign. We'll have b plus, again, 1 plus what? P plus 1 plus over Q plus 1. Here I have to change the symbols. Here we change the symbols. P, this is P, this is Q. You see, that much should be transparent. When this summand over here flies to the right-hand side of the equal sign, negative sign becomes plus. B is a common factor. Take it out. 1 plus what? P plus 1 in the numerator, Q plus 1 in the denominator. This is it. And then again, it comes out to what? Q plus P plus 2 in the numerator, Q plus 1 in the denominator. And once we flip that ratio, then we have what? Q plus 1 and Q plus 1 cancel each other out, but we will have what? B, this time don't forget B. B times P plus Q plus 2 for the free floating term. Now, the integral j of P and Q comes out to the left-hand side with a negative sign. So here we pay attention, it's negative sign. The factor of A, and then basically our fraction that was sitting in front of the integral j of P Q plus 1 flipped upside down. Q plus 1 goes in the numerator. B times P plus Q plus 2 goes into the denominator. And then our integral P of P and Q. That's it. Here I showed in red the deviation from the previous step. We uniformly, meaning mechanically, we roll through this relation and iterate Q down by 1. Replace Q with Q minus 1. So here Q minus 1 plus 1 becomes Q. And this is what we have here. On the right hand side, what do we have? A plus B times Z remains the same. The exponent of this linear combination does not depend on Q, percolates down as it was, P plus 1 times Z, but this time here Q becomes what? Q minus 1 plus 1 becomes Q, so Z raised to the power of Q. We pay attention. What's going on in the denominator? B remains the same, it's a constant. P here remains the same, but Q becomes Q minus 1. Minus 1 collides with plus 2, plus 1 comes out, P plus Q plus 1, same thing. Minus sign again, we carefully bring down minus sign. A, same thing. B, same thing in the denominator, A in the numerator. But Q plus 1 in the numerator becomes what? Q becomes Q minus 1, Q minus 1 plus 1 becomes Q. And in the denominator here, the same thing unfolds. P remains the same, Q becomes Q minus 1, minus 1 bumps into plus 2, plus 1 comes out, P plus Q plus 1 times what this time? Our integral j of P and Q becomes what? The integral j of P and Q minus 1. Q minus 1. This is how we iterate things down. So this time, if Q is positive, sits somewhere above 0 way here, we iterate it down by an arbitrary whole number, this time by 1, until we bring it down to the vicinity of 0, plus 1, minus 1, somewhere in there, hoping that the terminal case will be integrable in closed form, or the antiderivative of the function at hand will be expressible as a finite combination of elementary functions. This is it. So we now have four recurrence relations for our integral j, p, and q, depending on which one will we use when. Well, it depends on the specific material in the given integral, what's cooking over here, and on the values of p and q. But remember that we are in charge, we're in control. So for example, across the menu of 4 relations that we develop, we can twist or iterate one parameter, for example, down one way, and then we can obtain a certain integral. Maybe we can bring the other one, we can start iterating the other one down also, and bring the integral at hand, j, into something that is manageable and something that can be, hopefully, there are no guarantees to be sure, but if the given integral is computable or expressible as a finite combination of elementary functions, or can be expressed in closed form, then this technology of 4 recurrence relations, when we iterate things down or up, can simplify our life a lot. And as a first very straightforward example, I would like to share with you a simple computation. As a first and as such very straightforward practical sample application of the little bit of theory that we have developed in this episode, I recommend that you try your hand at applying that theory to the following integral that was solved by me some time ago. I took this integral on Quora. It was given by some of the people, and this is where I applied this little bit of technology. the integral I from 0 to 1 over x cubed times 1 minus square root of x, the whole thing raised to the 5th power, with the integration carried out over the variable x. Again, this integral can be computed in a number of different ways, but here's one straightforward step. We replace x with z squared. This will erase the pesky square root in the integrand, and we will have our favorite integral from 0 to 1. And what is the shape? 1 minus z raised to the 5th power times z raised to the 7th power. 2 comes from the fact that the first differential of x will be 2 copies of z times the first differential of z. And the rest is straightforward. We will apply this formula over here that we developed. Let's say we can agree this was our formula number 3, the third recurrence relation, where we argued that p, when it's positive, will iterate it down by 1. And what is the integral shown over here? What is this? Well, this is a specific instance of our differential when the constant a is 1, b is negative 1, p is 5, and q is 7. Now, between these two numbers, p is the smallest one, so the fastest way to reach a terminal case that we can handle is to start by iterating p down by 1. We use precisely this formula. This is what we developed, and that's it. There is no difference between using this formula for indefinite integrals or definite integrals. We basically put the boundaries of integration all over uniformly across, and game over. As such, we instantiate this bit of recurrence relation into here, first forgetting about the 2, just dealing with it directly. And we have what? Well, in this case, 5 plus 7 is 12, 12 plus 1 is 13. This is our 13. 1 minus z raised to the 5th power. Here, z is raised to the power q plus 1. 7 plus 1 is 8. But now look at this. Over the boundary 0 to 1, at the lower boundary, this free-floating term disappears because of the factor z. At the upper boundary of integration 1, this factor, the last factor, 1 minus z, disappears. So the free-floating term forever and ever vanishes. So we now have to deal only with what? With this substantive iterational piece here. 5 over 3 times what? The same version of the integral, but with p bumped down. So instead of 5, 7, 4, 7. And that's it. You should be able to handle the rest from here on your own. So now we basically run these numbers down. So a remains the same, it's 1. P is bumped down every time, 5, 4, 3, 2, 1. So now we have this p decrementing by 1 also. So 4 over 12 times j of what? 3, because 3 is 4 less, 1 less than 4, 3 and 7. So now we have 5 over 13, 4 over 12, 3 over 11, because now 4 becomes 3, 12 becomes 11, and this integral becomes what? Instead of 3, we have 2 and 7. We keep rolling, we have 2 over 10 as a factor, but now j is 1 over 7. And once we repeat this whole exercise, the last terminal case will be j 0 over 7. But instead of 5, we put 0, what do we get? We get the integral from 0 to 1 of just z to the 7th dz. I put it over here in small font, integral from 0 to 1, z raised to the 7th power dz. It will be, this is a trivial case, z raised to the 8th power over 8 between the lower boundary of 0 and the upper boundary of 1, 1/8. We put 1/8 over here, game over. So now we take this beautiful formation over here, we bring it over here, and we do not forget our 2. Don't forget the 2. And then a favorable wave of cancellations. 2 times 5 is 10. 10 in the numerator, 10 in the denominator cancel out. Here we have 4 and 2 is 8. Here is 8, 3 and 9. So once we cancel everything that can be canceled, it's arithmetic at this point, it doesn't really matter. It's 1 over 2. This is the prime factorization of this number. 1 over 2 raised to the 2nd power times 3, next prime, raised to the 2nd power, 11 prime, 13 prime, 5,148. Nobody cares about this meaningless number. But what is important here is that we did have to bring in our technical ingenuity into the process of developing the little bit of theory, the miniature sort of industrial strength approach to doing these things, to integrating binomial differentials. And once that ingenuity is out of the way and it bears fruit, what follows after that is purely mechanical. There is no intellectual voltage in this process. This is just mechanical iteration over a given recurrence relation. That's it. There is no need to show ingenuity or creativity. We just plug the numbers into our recurrence relation and go boom, 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 step by step, 1, 2, 3, 4, 5, and so on until we drill down to the terminal case. Terminal case is very favorable, problem solved. So this is the characteristic texture of this type of situations in mathematics, where a little bit of theory is developed with some ingenuity, and then when this theory is dropped on top of a given problem, this problem is solved mechanically. There is no need even to think in this case. Now, if you understood how the application of our little bit of theory in practice works, you may try to take the following integral on by yourself. For a slightly more substantive application of the little bit of theory that we have developed in this episode, you may try to take on or try your hand at taking on this following integral j sub n dx in the numerator, and then x squared plus a squared raised to the power of n, where n evidently varies starting from 1, 2, 3, 4, 5, 6, 7, and so on. A is a constant real number. Here you will have to decide on your own which of 4 recurrence relations you want to throw at this integral over here, but regardless of how you do it, the result is shown over here. This is the result that you're expected to obtain: 1 over 2n times a squared times x over the denominator here, plus 2n minus 1 over 2n times 1 over 8 squared times the integral jn over here. So this is the recurrence relation that you are expected to obtain. Again, here, what is the terminal case? Well, the terminal case is when n is equal to 1. n is equal to 1. We all know what that integral is. It's the arctangent of x over a, 1 over a. A is a constant, evidently. In this case, we see that it cannot be 0, otherwise the whole thing falls apart and becomes meaningless. So this is the integral j1. The integral j2 will be 1 over 2a squared times x over x squared plus a squared, because the power is, in this case, will be n will be 1, plus 1 over 2. We grab the a from here, square from here, we get a cubed. So here there will be a show of odd powers times arctangent of x over a. And just for the record, again, if we keep rolling, then j sub 3, when n is equal to what? N is equal to 2. So we will have 1 over 4 a squared x over x squared plus a squared squared, because now n is 2, 4, plus we unroll this integral j2 over here, j2, we unroll it, and this is what we get: 3 in the numerator, a times a raised to the 4th power in the denominator, times x over x squared plus a squared, plus, in this case, it will be 3 in the numerator and 8 times a to the 5th power in the denominator, times the arctangent of x over 2. And that means what? That means that for as long as our heart desires, for any finite whole positive number n, we can compute the value of this integral by carefully bumping down n by 1 and unrolling the resultant previous integral with the result that we obtained. And for the next challenge, you will also need the little bit of theory that we have developed in this episode. Our next challenge will be a problem in mathematics numbered S3E12. And in that challenge, we're asked to evaluate the following infinite sum, where the summation index n runs from 1 to positive infinity, and the structure of the summand is the following fraction: 1 in the numerator, and the denominator has the following shape: n times n plus 1 times n plus 2 times n plus 3, and so on, until the final factor in the denominator is n plus p, where p is evidently a whole positive number greater than or equal to 2. Again, this problem was given on Quora. I solved it some time ago, and we recommend that you try to solve this problem any which way you can, and then, as a hint, try to use the little bit of theory of integration of binomial differentials that we developed in this episode. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share my solution of the problem S3M8, in which I will use precisely the technology for integration of binomial differentials.